In section 4.3 we have the addition rule, which is what we use to compute the probability of A or B, which is defined as the probability that in a single trial either A occurs or B occurs, or both. And throughout this course, when we say A or B, it is implied to mean the inclusive or, meaning one or the other or both, as opposed to the exclusive or, which would be one or the other, but not both. Now this event A or B is referred to as a compound event, which is an event that combines two or more simple events. So it's a compound event. Now to see what's going on here, let's look at an example. We're actually going to pull this from a little survey we did in class. And we have this chart here that says for the males and females in the room what the favorite color was, or is, from the 6 primary and secondary colors. I could ask, what is the probability of selecting a random student whose favorite color is red, or a student whose favorite color is orange? Well, using the classical approach to probability, I simply add up the number of outcomes that satisfy this compound event. Well, here I have 5 outcomes, right? People in this case, but 5 outcomes that would say their favorite color is red, and 3 outcomes who would say their favorite color is orange. So that's a total of 8 students in the room who would answer yes to, is your favorite color red or orange? So 8 out of 28, which reduces to 2/7, or as a decimal, that would be 0.286 if we round that to 3 decimal places. Okay, well, we could also ask, what is the probability of selecting a student whose favorite color is red, or a student who is female? Let's think about that. I have these 5 students who prefer red. Actually, these aren't students, these are people, because I was selected in this survey as well. But I have these 5 people whose favorite color was red, and then I have this total of 13 people whose favorite color, or not favorite color, but 13 people who happen to be female. But we need to be careful here, because if I simply take 5 plus 13, then these 2 women right here, whose favorite color is red, get counted twice. Now, are those 2 women more important than everybody else? Well, they may or may not think so, but the reality is no, they are not more important. Everybody counts the same. If I'm selecting a random person in the room, then each of those 2 women that preferred red is just as likely to be selected as any other person in the room. So I can't count them twice. So what has to happen then is we have to look at these 5 people who preferred red, plus add in the rest of the successful outcomes that are female, but not add in those 2 that have already been counted. So that'll be 5 plus 11 successful, so a total of 16 successful outcomes. So 16 out of 28, which is equal to 4/7, which is approximately 0.571. Okay. Now, to further illustrate the need to not count people twice, let's look at another possible compound event here. Suppose I want to know what's the probability of selecting a student or a person whose favorite color is blue, or whose favorite color is green, or a person who's male. Well, we have a total of 15 males, and then we have a total of 6 people who preferred green. We have a total of 8 people who preferred blue. So if all we did was say, well, let's see, that means the total number of successful outcomes that are either blue or green or male is 15 for the 15 males, plus there are 6 successful greens, and there are 8 successful blues. Well, out of 28 possible people in the room that I could select, when I add this up, I end up with 29 28ths. Well, that can't be right. We learned in the last section that a probability of a sure event, of a guaranteed event, is 1. The probabilities can't be any higher than 1. This doesn't make any sense. If there's only 28 possible outcomes, then how can 29 of those 28 outcomes be successful? It doesn't work. Okay, so clearly if we try to count these values twice, these repeated values twice, it can definitely give us an impossible answer. So again, what we have to do here in this situation is we have to say, well, let's see, we can start with the 15 males. There are 15 successful outcomes that are male, blue, green, or red, blue, green, or male. And then I can say, well, who else, what other people in this room would be a success? Well, each of these 2 females right there who preferred green would be a success, and each of these 3 females who preferred blue would be a success. So 15 plus 2 plus 3 gives me a total of 20 28ths, which simplifies to 5 sevenths, or approximately 0.714 as the probability there. Now, one way we could check this is we could think back to one of the things that we pointed out in section 4.2. Recall that the probability of A bar, or the complement of A, is equal to 1 minus the probability of A. Now, we'll investigate this a little bit more in just a few minutes at the end of this section, but for now we can use this to check our work here, because the complement of blue or green or male would be the females who didn't prefer blue or green. That can be a little tricky to see there, but if that makes sense, then we can see, well, these values that are left that I didn't just select, right, well, that's 2 plus 2 plus 4 is 8. Right? So that's 8 out of 28ths. Well, 8 out of 28ths and 20 out of 28ths, those work out to give me the total 28 28ths. So if that makes sense, if you can easily see what the complement of this compound event would be, then you can use that to check your work sometimes, because together they have to add up to 1, because everybody gets counted. Again, we'll look back at complementary events and compound events in just a few minutes. Now this example sort of implies this intuitive addition rule, which says that to find the probability of A or B, first we find the sum of the number of ways that A can occur and the number of ways that B can occur, but we make sure we don't count, we count each outcome exactly once. In other words, don't count any repeated outcomes. And then, of course, using the classical approach, we simply divide by the total number of possible outcomes in the sample space. So that's what we did here. Red or female, we said, okay, let's find the number of ways that the person selected could be red, which was 5. And then we added in the number of ways that the person selected, could be B, could be female in this case. All 13 of these, but we have to make sure that we don't count them. We don't count any values, any repeated outcomes. We count every value exactly once. So if I take these 5 reds, I can't count these 2 females again. So I just add in the remaining 13. 11. Count the remaining 11, and we get that 5 plus 11, a total of 16 out of 28. Okay, well that was the intuitive addition rule, and then we have the formal addition rule, which is actually a formula that we can write out. It says the probability of A or B is equal to P of A plus P of B minus P of A and B. So to see this in action, let's look at that same color survey, and let's say what is the probability of, and we'll go with red or female again, but this time we'll actually kind of work it out formally here. According to this, that's going to be equal to the probability of selecting a student or a person whose favorite color is red plus the probability of selecting a person who's female, and then minus the probability that the person I select is red and they are female, prefer red. Okay, so let's look back here at our chart. So the probability of red, well, there were 3 and 2, so a total of 5 people who preferred red out of the 28 people in the room. And of the females, there were a total of 13 females out of 28 people in the room, so that's P of female. But then we have to subtract in the probability of red and female. And so the probability of selecting somebody who preferred red and it also was female, well, of these 28 people in the room, there were exactly 2 of them who were female and also preferred red. So we subtract that 2 here, or 2/28 rather. 2 people are successfully preferring red and female out of 28 possible. We work that out. 5 plus 13 is 18 minus 2 is 16 28, which is the same answer we got before intuitively. So we don't really have to use the formal addition rule a lot as long as we just remember not to count any of the repeated values. Let's look at another example here. We have a survey of a college reveals the following data. We have a certain number of Caucasian students and non-Caucasian students. We got males and females. That's all it's broken down into. Now here's what we have to do here. We have a scholarship that's designed to encourage women and minorities to pursue degrees in science. So if a student is selected at random from the entire student body, what is the probability that the student is female or non-Caucasian? Well, intuitively, that means I'm just going to add up not the 2347, but the 2125, because those are females, and they would meet the criteria. And the 1104 here, those are all females, and they're also minorities, so those would satisfy. So I add up all those females, and then I add up all of the non-Caucasians, but I don't want to add in the 1104 twice, because then I would be counting those people twice. You know, it's kind of like if I was selecting a random student and just giving this scholarship to a random female or minority, then those people that are female and minorities would have twice the chances of receiving the scholarship. And that's not really fair, so that's not how we do this. What we have to do, intuitively, is we're just going to say probability of female or non-Caucasian would be 2125 plus, there's 1104 of the female non-Caucasians, and the 1252, that's the rest of the non-Caucasians that we didn't count yet. And we divide that by the total number of possible outcomes in the entire probability space, which is simply adding in these 4 values. 2347 plus 2125 plus 1252 plus 1104, because if I select a random student, it's got to be one of that large number of students. So let's get a calculator out and see what we get. Let's throw it over there. And so we got to figure out what is the sum of all these. How big is the entire student body? 2347 plus 1252 plus 2125 plus 1104. And then I get 68, 28. That is the size of the probability sample space. So I go in here and I have to say, okay, fine, divided by 68, 28. Okay, well, let's add those first three numbers. There's three numbers in the numerator. 2125 plus 1104 plus 1252. 125, 1104, 12, yep. Okay, so we get 4481. Divided by 6828. Can I simplify that? I think I probably can. But really, for now, I mean, that might take a while to try and see if there are any common factors. So it's sufficient just to get that as a decimal, most likely. So we'll get back to our calculator. We'll say, okay, 4481 divided by 6828 is 0.656, approximately. So, if I selected a random student from the entire student body, the probability that that student would be eligible for this scholarship that's for women and minorities is 0.656 approximately. Okay, so really just one more definition here. If there are no outcomes that satisfy both A and B, in other words, if A and B cannot occur at the same time in a single trial, then we say that A and B are disjoint, which is also known as mutually exclusive. So different books tend to prefer one word or the other. This book tends to prefer disjoint, so that's fine, we'll go with that. For example, we could look back at that color example that we did. And some of these things are disjoint. Red and orange are disjoint events. Right? It's not possible if I select a single person, a single trial of this experiment, it's not possible to have that outcome have the favorite color red and the favorite color orange, because when we conducted this survey, we were looking for to just pick one. What is your one favorite color? No ties allowed. Everybody had to pick one. It's impossible for somebody to pick red as their favorite and also orange as their favorite in that context. So red and orange are what we would call disjoint events. And then we have a consequence here that if A and B are disjoint, then the probability of A and B both happening is 0. Well, that should make sense. If they're disjoint, that means that it's not possible for both these things to happen in a single trial. And if something's not possible, then its probability is 0. All right, let's look at some notation for OR statements and AND statements. Okay, so we can write P of A or B as P U B. Well, this U is really a union of those two events. And then we have the probability of A and B. We can write that as A. Now, I think it looks kind of like an N, but it really stands for intersection. Intersection. Well, an intersection, if you haven't studied these terms before, an intersection is where two things intersect. They overlap. If you're standing in the middle of an intersection on the roads, then technically you're in both streets at the same time. And then the concept of this union, is more of a, well, if you're in any one of these areas or events, in this case, then that counts as being part of the in part of the union. But anyway, those are the symbols there. You don't really need to worry about the union and intersection part. You just need to know that when you see this symbol, that means OR. When you see this symbol, that really means AND. And then we have, just another consequence of this, that if A and B are disjoint, then the intersection of A and B is empty. It means they don't overlap. They have nothing in common. Okay, well, by definition, A and A bar, the complement of A, are disjoint. This means that using the intuitive addition rule, we don't have to worry about counting any outcomes twice when computing the probability of A or A bar, because there's nothing that would be counted twice, because they don't overlap, they don't intersect. They're disjoint. The intersection is empty. Okay, so formally, probability of A or A bar, we would take P of A plus P of A bar minus the probability of the intersection. Well, since the intersection is empty, that means the probability is going to be 0. So I can just take P of A plus P of A bar. And furthermore, since every outcome in the sample space is either in A or in A bar, then every outcome would be counted. So probability of A or A bar is equal to 1. Well, that should make sense because A and A bar are disjoint, but they're also, we can use the word exhaustive. They exhaust the entire probability space, sample space. Everything is included. You know, if I said the probability of selecting a student whose favorite color is red or whose favorite color is something other than red, well, then everybody would get counted because everybody either has their favorite color is red or their favorite color is something else. So everybody would get counted there. And the probability of selecting somebody whose favorite color is red or whose favorite color is not red, it's got to be 1 out of 1. It's got to be guaranteed. And then, of course, since P of A or A bar is equal to 1, then, that gives us a couple of things, because if P of A plus A bar is equal to this thing, which is equal to 1, then that sum must be equal to 1. And then we get a couple equivalent forms of the same thing. That's section 4.3.